Today we are going to study a flash type analog to digital converter. This flash type analog to digital converter is based on comparing an unknown analog input voltage with a set of reference voltages. So this is the circuit diagram for a flash type analog to digital converter. Here we can see we are using a number of comparators and we are comparing an analog input voltage with a set of reference voltages. To generate this reference voltages, we are using a number of resistors. By using this resistive network, we are generating a number of reference voltages, and these reference voltages are applied to the inverting terminal of the comparator circuit, and to the non-inverting terminal the analog input voltage VI is applied. So here we are comparing an unknown analog input voltage with a set of reference voltages. Then to convert an analog signal into a digital signal of n outputs, 2 raised to n minus 1 number of comparators are required. For example, a 2-bit analog to digital converter requires 2 raised to 2 minus 1 number of comparators. That means 2 raised to 2 is 4. So 4 minus 1, 3 number of comparators are required there. Then to get a 3-bit digital output, we need 2 raised to 3 minus 1 number of comparators. 2 raised to 3 is 8. So 8 minus 1, 7 number of comparators are required here. So here we are considering a 3-bit digital output. So here we need 2 raised to 3 minus 1. That means 7 number of comparators are required. So here we can see we are using 7 number of comparators. Then to provide the reference signals, we are using this resistive network. By using this resistive network, a number of reference voltages are generated and these voltages are applied to the inverting terminals of the comparator, and to the non-inverting terminal the analog input voltage VI is applied. So these comparators are comparing this analog input voltage with a set of reference voltages. So before proceeding, let's look how these reference voltages are obtained. So consider this resistive network. Here we can see a plus VR voltage is applied at this point, and here we are using total 8 number of resistors. We have total 7 comparators are there, so we are using 8 number of resistors here. Then consider this first comparator. To the inverting terminal the reference voltage is applied, and this voltage is actually the voltage across this resistance R. Now the voltage across this resistance R can be calculated by using the voltage division rule. So this is the resistive network. Here a VR voltage is applied, all the resistors are equal, and we have total 8 number of resistors are there. So the total number of total value of resistance is 8R. Then the voltage across this resistance R can be calculated by the voltage division rule. VR into R divided by total resistance. So VR into R divided by 8R. That is the reference voltage at this inverting terminal. So what is that voltage? VR into R divided by 8R. So that is VR by 8. So VR by 8 is the reference voltage to this first comparator. Now consider the second comparator. When we consider the second comparator, the voltage at the inverting terminal is the voltage between this point and ground. Okay, between this point and ground we have these two resistors. So between the inverting terminal of the second comparator and ground, the total resistance is 2R. So the voltage at this point is the voltage across this 2R resistance. Now what is the voltage across this 2R resistance? By voltage division rule we can calculate it as this VR into 2R divided by 8R. So we will get 2 times VR by 8. Okay, so for the first comparator the reference voltage is VR by 8. For the second comparator the reference voltage is 2 VR by 8. Now for the third comparator it will be 3 VR by 8. That means it is the voltage across this 3R resistance. So voltage at this inverting terminal will be VR into 3R divided by 8R. So it will be 3 VR by 8. So similarly we can calculate the other reference voltages also. So for comparator 4 the reference voltage will be 4 VR by 8, and for comparator 5 the reference voltage will be 5 VR by 8, and for comparator 6 the reference voltage will be 6 VR by 8, and for comparator 7 the reference voltage will be 7 VR by 8. Okay, so these reference voltages are applied to the inverting terminals of the comparator, and to the non-inverting terminal the unknown analog input voltage is applied. Then the output of these comparators are applied to a priority encoder. Then depending upon the comparator outputs, this priority encoder generates the 3-bit digital output. This 3-bit digital output will be equivalent to this analog input VA. Okay, let's now look how this circuit works in detail. So consider the case when this input signal Vi is in the range 0 to VR by 8. That means Vi is in the range 0 less than or equal to Vi less than or equal to VR by 8. That means Vi is greater than or equal to 0, but it is less than or equal to VR by 8. Now consider this comparator 1. Here to the inverting terminal the reference voltage given is VR by 8, and when the input voltage Vi is less than VR by 8, the output of this comparator will be 0, because at the inverting terminal we have VR by 8 and this VA is actually less than this VR by 8. So voltage at the inverting terminal is greater, so the output of the comparator will be low, or we can take it as digital 0. Okay, then consider this comparator 2. Its inverting terminal is connected to 2 VR by 8, or the reference voltage to this inverting terminal of comparator 2 is 2 VR by 8, and this VA is less than VR by 8, so it is also less than 2 VR by 8. That means voltage at the inverting terminal of this comparator 2 is greater, so its output will be low or logic 0. Then for the all the above comparators, the VA value is less than their corresponding reference voltages, and hence the output voltage of these comparators are at lower levels. Okay, so the output of all of the 7 comparators are at logic 0 level. So that value 0 0 0 0 0 0 0, that value is applied to the priority encoder. Then this priority encoder will convert that data to the corresponding binary output. Now consider the case when the input voltage Vi is greater than this VR by 8 but less than this 2 VR by 8. Okay, that means this Vi is in the range VR by 8 less than Vi less than or equal to 2 VR by 8. So at that condition, consider this first comparator. To the inverting terminal of the first comparator VR by 8 voltage is given, and to the non-inverting terminal this VI is given, and this VI is now greater than VR by 8. So the voltage at the non-inverting terminal is greater, so the output of this first comparator will be high, or it will be logic 1. Now consider this comparator 2. The voltage at the inverting terminal of comparator 2 is 2 VR by 8, and we have considered that this VI value is less than or equal to this 2 VR by 8. So actually it is less than this 2 VR by 8. So voltage at the inverting terminal is greater, so the output of this comparator will be low, so it will be logic 0. And for comparator 3, what will be the output? We know VI is less than or equal to VR by 8, so it is also less than this 3 VR by 8. So output of C3 is also logic 0, and the output of all the above comparators are also at logic 0. Okay, so when the input VI is in the range VR by 8 less than VI less than or equal to 2 VR by 8, then the output of this first comparator is 1, and the output of all other comparators are zeros. Okay, and the priority encoder converts that data into its corresponding output. Similarly, by considering the range of this input voltage, we can calculate the digital output that we are going to obtain. Let's consider this case with the help of a table. So consider this table. This is the comparator and digital outputs for this 3-bit simultaneous type analog to digital converter. This flash type analog to digital converter is also called a simultaneous type analog to digital converter, because here we are comparing the analog input voltage with a set of reference voltages simultaneously. And also this circuit is also called a parallel comparator type analog to digital converter, because we are using a number of parallel comparators here. Okay, so let's now consider this table. So first consider these two columns. The analog input voltage is shown here, and here the outputs of the comparators are shown. So here we can see, as I said earlier, when the input voltage is in the range 0 less than or equal to VI less than or equal to VR by 8, the outputs of comparators are at logic 0 level, and the output of the priority encoder will be 0 0 0. That means the input voltage VI is less than VR by 8. So the output of all the comparators are at 0 level. Then when the input is in the range VR by 8 less than VI less than or equal to 2 VR by 8, in that case the output of first comparator is 1, and the output of all other comparators are at logic 0. So this is the input to the priority encoder, and the priority encoder converts this input data depending on the priority value. So here C1 is 1, so it has the priority, so the output is 0 0 1. Then consider the next case when the input is in the range 2 VR by 8 less than VI less than or equal to 3 VR by 8. So this 3 VR by 8 is the reference voltage of the third comparator, and the input voltage is greater than this 2 VR by 8 and it is less than this 3 VR by 8. So the output of first and second comparators will be high, and the output of all other comparators are at 0 level. Okay, and depending upon this input, the priority encoder will produce an output 0 1 0, because here C1 and C2 are ones, so the highest priority is for this C2. So output will be equivalent to that 2, 0, 1, 0. Okay, then consider the next case. When the input is in the range 3 VR by 8 less than VA less than or equal to 4 VR by 8. 4 VR by 8 is the reference voltage of comparator 4, and input voltage is greater than 3 VR by 8 but less than 4 VR by 8. So the output of first 3 comparators are 1s and the output of all other comparators are zeros. So here C1 output, C2 output and C3 outputs are at 1s and the priority is for C3. So the output will be 0, 1, 1. Then for the input range 4 VR by 8 less than VA less than or equal to 5 VR by 8, the output of 4 comparators are 1s and the output of the next 3 comparators are zeros. Okay, so the output will be, output of the priority encoder will be 1, 0, 0. Then for 5 VR by 8 less than VA less than or equal to 6 VR by 8, the output of first 5 comparators are 1s and the output of the 6th and 7th comparators are zeros. So here we can see the 5th comparator output is 1. So the priority is for that 5th comparator output. So the output will be 5 or 1, 0, 1. Then for input 6 VR by 8 less than VA less than or equal to 7 VR by 8, the output of 6 comparators are 1s and the output of that 7th comparator is 0 and the output will be 1, 1, 0. Then for input 7 VR by 8 less than VA less than or equal to VR, the outputs of all the comparators are 1s. So the output or the digital output that we get at the output of the priority encoder is 1, 1, 1. So depending upon the range of the input, we will get the corresponding digital output. Okay, when the input is in this range, we will get 0, 0, 0. When the input is in this range, we will get 0, 0, 1, like that. Okay, now when we consider this flash type analog to digital converter, the advantages of the circuits are: the simultaneous type analog to digital converter is the fastest because analog to digital conversion is performed simultaneously through a set of comparators. Hence, it is also called a flash type analog to digital converter. The typical conversion time is 100 nanosecond or less. Now, second advantage is the construction is simple and easier to design. Now, when we consider the disadvantages, the simultaneous type analog to digital converter is not suitable for analog to digital conversion with more than 3 or 4 digital output bits, because in that case we need actually 2 raised to 4 minus 1 number of comparators. Okay, that means for n bit output we need 2 raised to n minus 1 number of comparators. So this is a large number, so we require a large number of comparators. So it is not suitable for more than 3 or 4 digital output bits. In this flash type analog to digital converter, the number of comparators required doubles for each added bits. So it is not suitable for more than 3 or 4 digital output bits.